Yeah, okay, let's start. So we're happy to have David Saltman. Everybody knows you, David. So you can just start. The title is Cyclic Matters, right?
Yes, that's the title. Thank you very much. I thank you for listening. I very much regret that circumstances didn't allow me to be there today, but I would like to give this talk. So this concerns cyclic Galois extensions of commutative rings, not necessarily fields, and cyclic algebras. And there's a great deal of material here. So I apologize for going fast and not doing things justice. Let's start with the classic situation, which is the Artin-Schreier polynomial, x to the p minus x equals a, the Galois action. And I found, as I thought about these things, knowing the Galois action is the important thing. That's sigma of x equals x plus 1. It is a fact that this is true for commutative rings of characteristic P, not just fields. And that's going to be important to us. We're going to try to preserve that fact even when we go to sort of as much as possible when we do characteristic 0. I also want to make that this comment down below, which is that this is a fact that I didn't realize this until recently, and it should be better known, that if we're in characteristic P and our Galois group is a P group, then as a module over the group ring, S is always isomorphic to R of G. Since I wanted to prove one thing, I'm going to try to prove that. That's not where I wanted to be. There we are. So if you have inside the group ring, there's the augmentation ideal generated by all the elements G minus 1. And they're all nilpotent because you're in characteristic P. So for some power, these guys are 0. So you have an ideal generated by nilpotents, making this a nilpotent ideal. And the statement that S is isomorphic to R of G means that it has a generator. And so by Nakayama's lemma applied to the nilpotent ideal, all you need to know is that S mod I has a single generator. And S mod I, you can easily show, is just R. So this is a fact, as I said, I think should be better known. But what it says is that, let's go back to the slides. What it says, it's going to actually be key because in characteristic P, the Galois module structures are all understood. And in characteristic 0, it's complicated. So let's talk about the first easiest case in mixed characteristic, which is that we'll allow ourselves to have that's Z row algebra, not ZP. All our commutative rings will be Z row algebras. And there's a polynomial that you just show that this is makes sense, this definition, x to the p plus g of x. And the theorem is that this is a lift of the Artin-Schreier polynomial. So that if I take the adjoining a root of this, and I add the one more condition that 1 plus a to the p is invertible, then this is Galois, and this is the Galois action. Sigma of x equals rho x plus 1. Again, often they tell you if you give a talk, you should make sure the audience comes away with one thing. That's why I put it in the box. That's the action in characteristic 0 that lifts the Artin-Schreier action in characteristic P, and that's what you should take away if possible. The consequence of this is that if I have a cyclic Galois extension in R mod PR, and that's what R bar is, it lifts to a cyclic Galois extension in R mod of R itself, as long as I can guarantee that these 1 plus a to the p elements are invertible, which I do by assuming 1 plus a to r. All of those guys are invertible because I otherwise have no more control over them. Now, I put this as these slides of necessity are a month old and things have changed over time. you can always lift Galois extensions in it, even without the root of unity, even not assuming rho is an R, and may actually see why. But I wanted to jump because I wanted to, if I can't change the material, I'll change the order. Hidden in this argument that I just gave you, which I wanted to point out, is that if I have S over R is G Galois and G is cyclic of order P, then the group ring is actually, T to the is just mod out by T to the P minus 1, obviously, and that factors. What those factors are, of course, not relatively prime. So what happens is you can build up the group ring by an iterated series of fiber products, R mod T minus 1, R mod T minus rho times T minus 1, and etc. But you don't have to go far, because actually it will turn out over and over again. And what I'm saying that that all you have to worry about is the structure, not always over the group ring, but really over this image of the group ring, which is T minus rho times T minus 1, mod out by that, and that's enough to know everything. So in fact, that's the content of this theorem. The following are equivalent. My cyclic degree P Galois extension, isomorphic to RG, meaning it has a normal basis, which is equivalent to just this much simpler image, mod T minus rho minus T minus 1, being isomorphic to the equivalent quotient of R of G, and that is equivalent to this S being given by a polynomial. But there are more degree P Galois extensions, because in characteristic 0, S is not necessarily RG. So in fact, if I take a rank 1 RG of 1 projective, and then I have this one condition here, that this complicated condition that I wrote P of rho to the G is an element in the Picard group of this more complicated fiber product. That is when you can build a Galois extension from P1, such that P1 is the underlying module of S. S is in, and again, we're going to get a lot of mileage from the fact that G is abelian. We can talk about an uncomplicated Picard group for R of G, and S is actually an element of that Picard group. And this is the complicated fiber product. So the point being there is that there is a sort of an obstruction to P of 1 to a module being the underlying module of a Galois extension, and it's in the Picard group of this pullback. That's the way to put it. All right, so now how are we going to do higher degree extensions? Well, the way we're going to do it is degree P at a time. And so to justify that, let's start with this ring, which is, I'm going to take 0, which is the cyclotomic units in the cyclotomic field. Rho is always the pth root of unity. I adjoin an indeterminate, and I basically invert by what I need to make things invertible, and I form that generic versal mixed characteristic Galois extension S, and now this actually specializes to all of them, and this construction of S was where I started this project, because I sort of noticed in this paper of Suresh, where he was talking about H3 of curves over number fields, that he needed properties of cyclic degree P extensions, and he got them by implicitly invoking this polynomial. All right, so how does the generalization work? The generalization works, so now for generality's sake, I adjoin a bunch of indeterminants. I allow myself to invert by stuff that is both congruent to 1 mod eta, and eta, I'm not sure I mentioned this, eta is rho minus 1. Let me write it here. I got to write. Eta is rho minus 1. So it's a prime element of Z rho. And I'm allowing myself to invert by elements that are congruent to 1 mod eta and 1 mod the ideal generated by all of the x's. The point about all of that is that R mod eta R is a polynomial ring over the finite field, and essentially a very general ring. And here I have the full theory of all the nice stuff that happens in characteristic zero, in characteristic P rather, and R mod MR, by modding by the x's, I can get back to the coefficients. The second fact is a technicality. The Z rho has a large Picard group, and I want to be able to sort of correct for it. So it's useful then to be able to get back to Z rho by modding out by M. Now, suppose I wanted to construct a cyclic extension of degree, which was versal of dimension of degree P to the R. In some sense versal. I'm not actually sure the right sense. You do it in 2 steps. First of all, you take your original extension S over R, which I assumed had degree P to the R, and you build one of degree P to the R plus 1. And the second statement is you make whatever you just built generic. So it turns out it's hard to build T, but it is easy to make it generic. And the way you make it generic is you build your T and then you modify by a cyclic degree P extension of R in a very general one. That's what the point of this construction is. X is a new indeterminate. I basically write a new degree P extension of that, and I basically modify the original. And the moral is that the generic T is the special T times the generic P. Okay, so now the hard part then is not to make it versal, but to do it at all, to extend. And so in order to do that, we need a generalization of the Albert criterion that extends to rings. Basically, if I have an S over R with cyclic of degree P to the R, when does it have an extension to a cyclic of degree P to the R plus 1? And I will correlate if S is a field, this is the Albert criterion. If L over K is CPR, then it extends, there's an obstruction in the Brauer group. That there's the cross product L over K comma rho has to be trivial in the Brauer group. There's going to be more of an obstruction in our case, but we're going to be able to deal with it. First of all, we can't stick to the ground ring alone. We have to do something a little bit cleverer. Suppose I now start G is cyclic of order P to the R plus 1. C is the unique subgroup of order P. Tau is the generator of that subgroup. And I form the following as in my algebra whose center is not R, but the group ring R of C. And basically, tau, remember, is an element of C. So that's an element of the ground ring. Sigma is the automorphism of the cyclic automorphism. And I form that as a Maya algebra. That is almost the one that we care about most. I will point out that this is not so different from constructions that are common in ring theory. This is a twisted group ring. The point is that G doesn't act faithfully on S, so it's not your standard twisted group ring, but it's a twisted group ring. But as I warned you before, what's really important is not A, but I take A and I mod out by the, remember before it was T minus rho, but in this case, T mapped to tau. So it's my mod out by tau minus rho times tau minus 1, and I get a new cross product, which is a little bit closer to the Albert criterion, but it's over this one fiber product RC1. And rho, by abusive notation, is the image of tau. It will become a root of unity when I mod out by eta. All right, and so the Albert criterion is the following. S over R extends to one more higher cyclic Galois, which I write in that sort of triple way, if and only if, first of all, A splits, and the splitting P1 has to have extra properties. So it's a module over RC1, so I can mod out by tau minus 1. I call that P0. That has to be S. That's easy to arrange. And then the other criterion, which is harder to arrange, is that this analogy of this construction I did in the degree P case, what I call P of rho to the G, it has a G action. And once again, there's this Picard group here, a Picard group obstruction to extending. This P of rho is to the G is always in the Picard group of this fiber product, but in this case, it's a trivial element in the Picard group. It's a Brauer group condition and a Picard group condition. So then I added some notes. So suppose we actually want to use this. We want to take a degree P to the R extension and make a degree P to the R plus 1 extension, because that's in our process of making versal cyclics in mixed characteristic. So first of all, we can reduce to the case that the bottom ring is regular, because in fact, it's going to be something fairly simple, a localization of Z of rho, adjoin X, and localized at some elements, 1 over some stuff. So it's regular, therefore any Brauer group condition we can deal with at the field. That is, the Brauer group of a regular ring embeds into the Brauer group of its field of fractions. In fact, what we will use in the actual proof is that it embeds into the Brauer group of R with eta localized, 1 over adjoin 1 over eta. So we deal with the Brauer group at the field level, and we localize to deal with the Picard group. It will turn out that the Picard group is sort of a double condition, but I don't think we have enough time for that. But let me talk about some of the ideas that appear in the proof. I just mentioned that, the old Ibert. Also, the Picard group of R, because it's a localized polynomial ring over Z rho, is actually the Picard group of Z rho. And I make 2 comments about that. First of all, the map on units is surjective. And secondly, the Picard group mod eta is a polynomial ring. That's trivial. When I made these notes, it was a conjecture. Now it is a theorem. And the theorem is that if I have a cyclic degree P to the R over R mod, this here is little p, capital P is little p times R, then every degree P to the R cyclic lifts to a degree cyclic of the same degree in the mixed characteristic case. The important note here is that I never actually needed all those indeterminates. As I said, these are old slides. I only needed one indeterminate. I need the indeterminate that you start with to have your degree P extension. Artin-Schreier polynomial has one parameter. The lifted one with that G x to the P plus G of X had one parameter. That parameter is X. So this is into a 2-dimensional regular ring. And that is important because for 2-dimensional regular rings, reflexive modules are projective, and that will be important. Okay, so now let me go back to almost cyclic algebras. All right, so if you're me and you just have written down a new way of describing cyclic extensions, you almost automatically need to write down the corresponding new way to describe cyclic asymptotic algebras or cross product, cyclic central simple algebras. I also want to point out that this project had me going back to my thesis, which I'm apparently willing to admit was in 1976, some years ago, and seeing new things in my thesis that I missed entirely. So, age doesn't necessarily totally degenerate your brain. What I showed in my thesis was that the Brauer group of elements of order P or order dividing P, over an arbitrary commutative ring of characteristic P was also well behaved, just like the cyclic Galois extensions. And it was in fact generated by what I call differential cross products, but forget that term because it leads you astray. These algebras that generate are basically generated by X and Y subject to the condition of xy minus yx equals 1 and x to the p and y to the p are central. That's why I thought it was a differential in there. This is y inducing a differential on the extension adjoined by x. And so we'll call that algebra bracket AB. And one of the things that, again, makes it much different than characteristic 0 is that this is always azimuth. It doesn't matter. It's azimuth even if A and B are both 0, and certainly if their product is 0. But of course, if one of them is 0, it's a trivial azimuth algebra, but it's still unramified. It's still, and this is the surprising observation that I missed so long ago, which is that in this algebra, xy still satisfies xy to the p minus xy is central because such a polynomial is always Galois. This is a Galois extension of the center. And so instead of thinking about these algebras of differential cross products, I want to think of them as almost cyclic algebras. And I know almost because I have a Galois extension, but I don't have the invertible element inducing the Galois group on the extension. Nonetheless, by the way, these Galois extensions split AB, which shows that unlike in characteristic 0, in characteristic P commutative rings, every element of order P in the Brauer group, and hence by obvious generalization, every element of P power order in the Brauer group is split by an étale extension. All right, so let's talk about these algebras and why I call them almost cyclic and what's going on about them. So if you think about it, X is not invertible, but X induces, let me put it this way, X times alpha is sigma of alpha X for alpha in the thing generated by XY, even though X is not invertible, you have that. And so that means that X will be on the one will live on this upper diagonal, assuming you picked your bases right. Y is the reverse, alpha Y equals sigma of Y sigma of alpha, and that puts Y on the lower super diagonal of in the split case. X times Y is a separable element. Now, it might be singular, but it's never too singular because it's separable. It has distinct eigenvalues, and that means it has rank at worst p minus 1. So that, of course, implies that X and Y have rank at worst p minus 1, and more than that, they're the places where there's zeros. I mean, the rank of X or Y are the number of zeros in the super diagonal plus A and the subdiagonal plus B. That's Y, that's X. And the number of zeros is the rank. And so basically you can arrange things so that this is X down the diagonal, and over here, that's X. A might be 0, but all the others are not. And down this diagonal is Y. They can't be 0, but B can be 0. And the fact that X comma Y, that original algebra, was azimuth in all circumstances is reflected in the fact that if I have all of the diagonal matrices and I have this one super diagonal matrix where B might be 0 and one subdiagonal matrix where A might be 0, or the other way around, I generate all matrices. The super diagonal gives me all the upper stuff, and the subdiagonal gives me the lower stuff, and I get everything. And that's basically why that algebra was azimuth, or another way of saying is that in the split case, Rxy, X and Y generates the full matrix ring. All right, we want to generalize this and to generalize it correctly, you need to know what's important and what's not. And as I mentioned already, differential cross product is not important. It turns out characteristic is not important, characteristic P. What was important about this discussion was that Rxy over R was cyclic Galois, and that X times Y had rank bigger than or equal to P minus 1. They didn't need to generate, they just needed to have rank bigger than or equal to P minus 1 no matter what. I will also mention that degree P made no role in this picture. This picture of subdiagonals and superdiagonals and diagonals, it was N, any N works fine. Okay, so the characteristic example of the same phenomenon is, again, we start with a Z row algebra. AR is generated by X and Y, and now we have this relationship, XY minus rho YX equals 1. And we call that algebra A comma B sub rho. That, of course, in characteristic 0 is not always azimuth, but the condition is very similar to before. 1 plus AB, eta to the P has to be invertible because that's what makes XY Galois. And if you have, you want to take a second thing home from this talk, this relationship, XY minus rho YX equals 1 is the right thing to take away. This, by the way, is also almost cyclic in the way that I'm going to make formal in a minute. But meanwhile, I have this theorem that not only can I always lift cyclic degree P Galois extensions, I can always lift order P elements in the Brauer group. Again, assuming some unit, 1 plus eta R is invertible, then this is surjective on elements of order P. And now, what does almost cyclic mean? Let's look at the example of AB rho. Let S be the Galois extension, which is Rxy. This, by the way, was supposed to be a P up here. And you will notice that, as I pointed out before, just as in this case, X induces sigma inverse written this way, and Y does the reverse. So if I look at the subspace, R module of A, the A that we were talking about, which has that action on S, then X is in there. And if I look at the sub-object that has that same action on S, then by obviousness, Y to the P minus 1 is also in there. Now, the matrix argument I gave before, when you look at what it all really means, it shows that P sigma times P sigma inverse is actually all of R. This is actually S, and this is S. And that says that pick, by a standard argument from about invertible ideals, that pick is in pick S. And so that's actually what was going on in the differential cross product. In both these cases, this P sigma was an invertible module over S, was a rank 1 projective over S, and we had these conditions that it times P sigma inverse was S. One of these implies the other, so you only need to assume one. And that's what an almost cyclic algebra of degree P will be. S over R is Galois, I is in pick S with this statement, and we form the algebra basically as a direct sum of S, I to the P minus 1, and we used phi, this isomorphism phi, to tell us how to multiply. So every rank 1 projective over S gives me an azimuth algebra, which is what I call almost cyclic of degree P. And as you'll see later, the degree P part was easy to ignore. But remember, my ultimate goal is to lift algebras of from characteristic P to characteristic 0. and it's very hard, as far as I know, to lift Picard group elements. But let me make one more comment. I find it fascinating. This is just to think about. As part of all of this argument, this one here, I have this two generator element, this ideal over S, which is generated by two elements, X and Y to the P minus one. Just assuming these conditions, I get a Picard group element. I have examples where it's not trivial. So I have a non-trivial Picard group element, and that somehow ought to be a natural element, but I can't figure out how. Okay. This is what we've already talked about. So now this is what we've talked about. So now degree P to the R, almost cyclic Asimov algebras. What we're going to do is we're going to mimic what we did in degree P. We're going to start with a G Galois, where G is now a cyclic of order P to the R. We're going to assume we have an element J in pic S whose norm into R is trivial. And then we're going to define this Asimov algebra as the quotient of a sort of a universal Asimov algebra. You take the subgroup of the twisted polynomial rings where you just allow JT and JT squared, etc. And then you mod out by the ideal, basically, that forces phi to be the multiplication. And this is obviously in pic S, and you mod out. And this construction generalizes the almost cyclic constructions, the specific ones I told you about AB and AB rho. So that's all very nice. Once again, Picard group elements are too hard to work with if you want to lift. So we're going to have a special case of that, which is we're going to define it as an order inside a central simple algebra, because it's most convenient to do that way. But you can define it as in generators and relations if you choose. So we start with R as a domain, and SO of R is cyclic with Galois group G. And we start with this cyclic algebra, and we have in B, we have elements such as X to the N equals A, Y to the N equals B, and basically XY is in S, because X and Y anti-commute in opposite ways. So X times Y commutes with S, and therefore it's in S. And though, so of course, what happens is that AB is the norm of alpha, is the norm of XY. And one more condition, the condition that makes this the appropriate thing in the Picard group, projective, is the condition that SA times S alpha times S times the adjoint of alpha plus S times B, the ideal generated by those four elements, is actually all of S. And that the adjoint is just all the conjugates, the product of all the conjugates except alpha. And that condition will make the order generated by S, A, X, and Y be Asimov, if and only if. And the argument is very similar to what I did before. You look at the set of things which anti-commute with S in two ways, and it turns out when you do that X, of course, is in J sigma, Y to the N minus 1 is in J sigma, the opposite, Y is in, etc. You do the computation, the product of those things is exactly that. So that shows that this is in pic S, and that's the condition you need to be almost cyclic and to be Asimov. Let us look at this condition a bit. This is also almost too hard to verify. And I will notice that you notice that if you want to show S is generated by 4 elements, it's enough to show that it's generated by 3 elements. So this is a stronger condition, but of course is good enough that alpha and adjoint alpha and A generate S together. Now, let's look in S mod AS. In there, alpha and adjoint alpha generate S. If that's S bar, they generate S bar. Well, what does it mean for alpha and adjoint alpha to generate S bar? It actually means that alpha always has rank bigger than or equal to n minus 1. If you go monomaximal ideal and the determinant of alpha is non-zero, it's of course non-singular. It gives you everything. But if not, then the adjoint is non-zero. And so this is the reappearance of that condition that XY had rank bigger than or equal to, in that case, P minus 1. All right. And so the way we're going to do this is how we're going to construct these algebras is we're going to basically write down cyclic Galois extensions, which are split direct sums of copies of R mod AR when I mod out by A. Because if it's a direct sum of those copies, then I can find my rank n minus 1 element by sticking a 0 in one place and units in all the other places. And then, because that's a complicated operation and I don't really know how it works in the Brauer group, I am going to point out that if R is regular, I don't care. The Brauer class of this algebra only depends on S and A, because that determines the Brauer class at the field. The B is irrelevant, the alpha is irrelevant at the field. At the field, it's a classic cyclic algebra, and so it only depends on that, and therefore we are okay. So and now what I basically want to do is 2 things. I want to, and I'm going to have to do this in words. I don't have the slides. I want to say that I can lift cyclics of any degree, and I pretty much outlined how you do that. You use the generalized Artin criterion to extend your original generic cyclic to something arbitrarily large. That is a very hard argument, I have to tell you. That was the sticking point in the whole thing. And then but once you have a cyclic defined over a polynomial ring, you can always lift it. So it's always good. So now the almost cyclic algebras will solve a problem which I was always sort of curious about, which is, in my thesis, I proved that if R is a commutative ring of characteristic P, then Brauer R was P divisible. And I always wondered to make that concrete. That is, if you give me the algebra that I really cared about was these algebras, A, B, because they generate the order P part, that should be a P to the R times B in the Brauer group, because it's divisible. And the question is, what is B? Can you describe it? And basically you do it stepwise. You can suppose you have an algebra of degree P to the R, which this suitable means that mod out by A, alpha has the rank bounded bigger than n minus 1. If they're suitable, then you can extend S to T over R, because we're in characteristic P, and we can therefore make a new almost cyclic algebra and verify that P times B is A. Keep doing that, and you get the general result that you can write down an Asimaya algebra whose P to the R times it is AB in the Brauer group. Why is that important? Well, it's because those are the algebras I'm going to want to lift. If I want to show the map on Brauer groups is surjective, then it's not enough to lift the elements of order P. I have to lift essentially PDR, arbitrary PDR roots of the elements of order P. If I can lift all of those, I can lift anything in the Brauer group. And that's why these almost cyclic algebras are important, because they are the PDR roots. And the fact is, I can lift the cyclics, and I take care, and I can lift to preserve this sort of almost cyclic condition. So then this is true now. Not a conjecture, it's true. Brauer group of R to Brauer group of R mod eta is surjective on P primary parts. So, and the reason is because I can lift almost cyclics. And the reason I can lift almost cyclics is because I can lift cyclics. All right. Now, you can eliminate this condition. This is also fairly new. And you do it in the way you would imagine, which is, you will notice that this whole technology about almost cyclic algebras basically never mentioned the root of unity. It mentioned the cyclic Galois extension, and it mentioned these things of rank and all of that kind of stuff, but it never mentioned the root of unity. So if I want to lift algebras and cyclics without assuming about a root of unity, then I only have to lift the cyclics, because the algebras had nothing to do with roots of unity, the almost cyclic algebras. So that's the problem. How do you lift cyclic extensions? I know how they behave when I join a root of unity, how the pth root of unity. How do I lift them in general? Well, clearly what you'd like to do is use the co-restriction. You would like to use the co-restriction and say, well, I've made it over Z rho, now I take its co-restriction. That gives me something over Z algebras, and I'm home free. The problem about using the co-restriction is that 0 over Z is not atal. So the co-restriction becomes problematic when you try to co-restrict over non-atal extensions. It is definitely degree P minus 1, which, as earlier talk said, is a saving grace, but it is not atal. So how do you do it? And the fact of the matter is, you can do it in general because of the thing that I mentioned at the beginning. Z rho X localized at a whole bunch of stuff, and I don't want to talk about exactly what I have to localize that, is a regular ring of dimension 2. And since it's a regular ring of dimension 2, reflexive modules are projective, and that means I can actually pull off, I can define a co-restriction, and I can show that the obstruction to the co-restriction being well defined is that you do what you usually do. You take a bunch of tensor products of it, and then you take an invariant object. And the problem is that you need that thing to be projective, and it isn't in general. But it is if it's reflexive, and you just get away with it because you only needed one indeterminate in all this game. So that means that I can use a co-restriction argument to do my lifting over arbitrary commutative rings. I still need 1 plus PR is inside R star, but in those circumstances, I can lift all cyclic extensions, and I can lift, and the Brauer group map is onto. All right, that's more than enough. Thank you very much.
Yes, but if somebody wants to ask a question, then she or he should approach the mic.
I guess I should ask for questions.
Yes, so who has a question?
let me warn you that
I'll give you an example. Let's see this way. So hi, David. It's Adam.
hi.
Can you use this lifting thing to obtain results for characteristic P fields that have been obtained already for characteristic 0, like, I don't know, some bounds on the symbol length or chain lemmas and stuff?
I never occurred to me because characteristic P is better than characteristic 0.
Usually,
you have better symbol bounds and all of that. You know, in characteristic P, the number of symbols is just the P rank of the field.
Yeah, that's true. Yeah. So perhaps the symbol length is not a good example, but chain lemma, for instance, is the way to take, I don't know, Rost's chain lemma and translate it to characteristic P using this lifting?
That question never occurred to me, so I'm not even going to begin to attempt to answer it, but that's an interesting idea. I will mention, just because I have the floor, I will mention another interesting idea. Embedded in all of this is a theory that I do not have. That is, I got around, but I don't wish I had, which is mixed characteristic ramification. I had to play games because I didn't have a theory of, of when is an Azamaya algebra ramified at a prime in a mixed characteristic situation. And that might be related to your question too. I'm not sure, but that's, when somebody asks me what next, that's actually what's next for me. To see if I can pull out of what my arguments a mixed characteristic ramification map.
Okay, thank you, David. Other questions? Yeah, Oya is coming.
Let me repeat. Louis, is that you?
No, it's Uriah.
Uriah, before you ask your question, let me repeat what I told you privately, Louis. When I made that matrix argument with the super and the subdiagonal, I had you in mind because it's closely related to some conversations we had. Neither of us want to say how many decades ago. All right, Uriah.
Sure. There is, I believe there is an open problem that asks if you have a local ring R and with a residue field K, does the map from Brauer group of R to Brauer group of Ks onto? So do your results, I don't know, give new results on this conjecture?
Well, so that one is only open as far as I know. Oh yeah, right. It's only, you need roots of unity. First of all, I'm guessing it's not even true if the residue field is characteristic P, because there are counterexamples. This is the usual counterexample to the, there's no unramified extension of Q. I'm having a senior moment, but it's the standard. Anyway, you can't lift the unramified degree 8 cyclic extension of F2 to Q, to Z2, basically. You can't lift it. So I suspect, first of all, that you want to ask your questions when P is odd.
Okay.
And then I don't know. It's obviously, once again, something to think about. There's some, this is, I think this is going to give lots of people, hopefully a lot more than me, things to think about. It does, to my mind, again, I thought about it differently. It explains, it sort of shows that Brauer groups in characteristic 0, if you just localize a little bit, are fairly large, because we know Brauer groups in characteristic P are fairly large. They're divisible, all this kind of stuff. And let me make one more comment. I lift the elements one by one. The characteristic mod P, the Brauer group is divisible. I do not prove anything about divisibility in characteristic 0 because I have to lift them one by one, and I can't lift them all infinitely simultaneously for the moment anyway. Maybe I can, but I can't at the moment. So I do not know that the property of being P divisible sort of translates up to mixed characteristic, but it would be interesting to know. Anyway, that's a non-answer to your question. Sorry.
Oh, yeah. Thank you.
Any other questions, guys? Okay. We'll thank the speaker again.
Thank you.